you. Good morning, everyone. Yes, so as my colleague explained, I'm scientist and AIT. And for those who don't know who we are, this is our booth. We are the Austrian Institute of Technology. This is Austrian largest research and technology organization. So we are over 1,400 employees with different competence units. But in this case, we are high performance vision systems. We do different inspection-based AI methods, high-speed sensing, and our novel technology, which is called inline computational imaging, which I will explain later in detail. As a research center, we have different research projects, and in this case, I will explain about a project that we are currently working on in a plasma environment, plasma welding, and what is plasma welding, or more specifically, additive manufacturing. So in this case, is similar to 3D printing, but with metal, where we use a very high power source to melt the metals, basically, and deposit in different layers. And with a robot, we create the path. And in this specific project, we are working with wire arc additive manufacturing. So there is a metal wire that with a very intense plasma we melt, and this wire gets drops, and the position of these drops can create things like the one that you can see here on the bottom right, basically. And the benefits of additive manufacturing is that it enables really fast deposition rates, and it saves a lot of time and material, because basically you can customize your design, and you don't have to build the entire part. You build just the parts that you need, and you can mill it. And this is an example here. And I don't know where's my pointer. And this is what I explained. Basically, we have a plasma torch here with a very high intense plasma and a wire. And as you can already expect, monitoring this is difficult, but it's very important, because having like a reconstruction of the molten piece of the welded part is good for quality control, so we can see the consistency of the part, if it's well produced or bad. We can improve and optimize the process inline, and measure again the accuracy, see how many deviations we have for the original CAD model or the original idea, and of course improve safety and automatization. And coming back to the plasma topic, you can expect that the main problem is the plasma itself, because it's really bright and it's very hot. So there is like this working environment is not the best for cameras, lenses, or any electronics due to these high temperatures, and more specifically for sensing methods based on vision. Plasma is extremely bright, so the people who do welding, they always have to wear this mask, because you cannot look directly with the eyes. So with a normal camera is the same. You cannot look directly into the plasma, because you won't see anything, because mostly plasma interference has a wide range of wavelengths, so it's in the entire visible range, and it's really intense. And this also usually the material that we use are metallic, always metals. So this makes even more complicated, because there is a lot of shiny reflections and metallic surfaces, and also the geometries are not always the best to be scanned. So how we approach this in this project, AIT personally, as I said, we have our AIT ICI technique. So if you were not here yesterday, you can maybe talk later to my colleagues, because we have two demonstrators here that show how this technique works in a smaller range, not for welding. And the way this works is we have some optical components like cameras, lenses, and so on. And basically, it's a software module that we have developed and improved over the last years. And this is a combination of light field imaging and photometric stereo. So basically, we move the object under the camera and illuminate from different directions. And by looking at the object from different perspectives with the camera, we can have a 3D reconstruction, so we can estimate the depth. And with the multiple illuminations, we can also reconstruct the surface normals of the sample. So this was presented some years ago here in Vision. We got Vision Award nominee and some other prizes, but this is based mostly, as you can see here, on hypercentric projection. So basically, when the object is traveling under the camera, there is this parallax effect. So the things that are closer to the camera travel at different speed than the things that are from the camera. And we can extrapolate more or less what is the position of these things traveling in a parallel plane to the camera. So I think as I say, we have some demonstrators here that you can look later. But we never tried this demonstrator with welded parts, with metallic and shiny welded parts. So first what we did was taking some plates that we weld, or like our partner welded in this project just for some tests. But this is without plasma presence. So this was done in our lab just to see if we can scan these parts. And you can see here that we get a very fine 3D point cloud where we can see this different welding lines with different, in this case, our partner wanted to try different machine parameters. So you can see these lines have different heights, different lengths. There is also like a gap here that some parameters were wrong. And the benefits of this is that we can have a 3D point cloud of the weld and extract different, as I say, parameters like the height or the profile of the welding seam. But of course, you will say, yeah, this is not in situ. This is just in your lab. Can you do this in presence of plasma? So this system, it's as you can see here, is quite compact, but it's not so easy to implement it in a welding machine. So at the beginning of this project, we developed a portable ICI. So this is a system that we can move and place in the machine. This is how we build it. And you can see that you have two holes on the side, so you can move it, place it in the machine, and scan. But the main problem that we have in this project is that the welding machine is really big, really bulky. And there's like the robot head, a lot of cables, the wire, the plasma torch. So we can not so easily implement this in the machine. So for this, we did an experiment where we didn't do it inline, but we were welding a cylinder or a semi-cylinder. And every 10 layers, we were placing the scan and scanning. So you can see this was our 3D model. And after 2.5 millimeters was the first layer, and then every I think it was 5 or 10 layers, I don't remember now, sorry. But yeah, we were stopping the welding process, placing this into the chamber, doing a scan, and taking back and continuing. So it's a start and stop process, but it was really nice already to see, like, to get a 3D scan in the machine of this welded part. And with this, we could extract, for example, the profile of the weld seam over the different layers and do some analysis. This was really helpful for our partner in this project. And we also tested with another weld, as I said. This was not in presence of plasma, but right after in the machine. And we can see here also like the weld plate in 3D. So this is the albedo. And ITZY, our system, since it uses a color camera, we can extract also the texture in 3D of the sample, so we can see the colorations or oxidations on the welding part, and also extract the height of the width and detect defects like here that we can see on the 3D point cloud in the texture, but also in the depth we can see that there is a gap where the wire was not depositing the layer. So after this, the main question, can we do it with plasma? Which, as I said, is the main challenge in additive manufacturing inspection. So for this, what we did was having a welding camera that uses an external laser. So this is a laser that is stronger than the plasma itself, and we place a filter. And you can see here that this represents the brightness of the plasma. This is the bandpass filter that we put, and with the laser illumination, we can illuminate this. So the way we did it was mounting the camera right behind the plasma torch, focusing at the welding seam, and I think this is not working. This is working. And this is how it looks like. So this is already with plasma, but since this laser is so intense, we don't have brightness from the plasma, although we still have reflections from the metallic surface of the weld plate. And this, as you will see next, is a challenge. But this is already with plasma. We recorded this. We feed it into our ICI algorithms. And as you can see here, we got something, which is really nice. As I mentioned, there is reflection, so that's where this part is missing, because this was saturating the camera due to the direct reflection of the laser. But still, we were able to reconstruct the topology of the welding seam. And from here, we could do some post-processing, like extract the welding width, the height, and so on. And for this, we did another experiment where we were depositing, it was a wall, and we were depositing many layers and scanning this inline. And you can see here the results. So this shows the confidence and the depth. Unfortunately, we were missing some parts due to the buffer being full. But you can see here, these are like the 3D maps look from the top and from the side. And for every layer, we can see that it is going up, up, and up. And this is, as I say, with plasma inline during the material deposition itself. So in conclusion, as I said, laser welding is a big challenge for inspection. There's still a lot to do. We are still having a lot of ideas and a lot of things that we want to try. But in this case, in this project, we wanted to see if our ICI 3D technique was capable of doing 3D monitoring. And it's a preliminary result, but we are hoping to have more future work on this and improve the robustness. So with this, I want to thank you, everyone. If you still want to know more about ICI, I will be here. My colleagues are here. And if you want to know more about arc welding scenarios, my colleague Thomas Michno, he will give a talk here tomorrow, but not about 3D, but 2D monitoring. Thank you.
Good morning, ladies and gentlemen. Thank you for joining the speech about lenses. Thank you for introducing myself, so I can cut the next foil quite short. So I'm working at Josef Schneider Optische Werke GmbH, so let's call it short Schneider Optics, so for many, many years. And we are designer and manufacturer of lenses, optical filters, and other optical components. And I would like to speak a little bit about the role and the importance of a lens in a vision system. So that's still our company. You see, we can do everything on our own. We have all capabilities in-house, which is really beneficial for many, many projects, standard projects, commercial projects. So what's a vision system? A vision system comprises of several components. Of course, you need light, mainly artificial lighting in typical industrial applications. You need a lens, because you need to form an image, which is imaged on the sensor of the camera. So you need, of course, a camera, and you need afterwards also some software for the image processing, so that you get the results out that you want to have. That's quite simple, that's quite obvious. So, what is the typical lens selection process based on our experience? The vision system designer is typically no expert in optics. And you know by yourself, what you don't know, you leave behind. You take care first for the things that you know. So you choose an illumination, you choose the camera, you may have the electronics, and at the end you see, oh, I need a lens. I calculate the focal length. I need a 25mm lens. It doesn't matter. There are so many 25mm lenses around. I don't take care. And only in the last moment, you buy a 25mm lens, you put it on the camera, you get an image, you're happy, but you don't know that you waste a lot of your potential result, because a lens is not a lens, and a 25mm lens is not a 25mm lens. There are so many differences also between manufacturers and also within the same manufacturer. So what should you do? By the way, I love this picture. It's not our R&D manager, I can tell you. Yeah, okay. You choose first the illumination. You can do, but then you figure out, oh, I don't find a lens that is suitable for the spectral range. You can choose first the lens. Oh, damn. I don't find a sensor with enough resolution. You choose the sensor or the camera first. Okay, oh, there is no suitable lens for it. And of course, it doesn't make sense if you choose first the software. Typically, you should have first the hardware. So, what should you do? You should consider every component in the vision system with the same performance, importance. So, you should choose them as a package. You have to weight all characteristics of all simple components, so together that they form the best possible result. And this of course includes the lens. Don't leave the lens at last. Consider the lens together with all other components when you design a vision system. That's of extremely importance for the final result of your total system. So, as we said, vision system designers are typically no lens experts, and all lenses look somehow the same. This is a kind of a checklist, and you ask for every point, what do I really need when selecting the final lens? And of course, there are some optical characteristics like the image size, which is defined by the sensor size. Of course, the resolution of the lens, which is defined by the pixel resolution of the camera, or if it's really high, the resolution that you need in your object. There are, of course, other things that you have to consider optically, like, for instance, the light efficiency. But there are also many other restraints that you have to take care of. You have to take care, for instance, also the mechanical interface. It's also simple and obvious. If you have a C-mount camera, you should have a lens that can adapt to C-mount. But you have to consider also size and weight. If you have limitations in your system, you cannot choose every lens. Maybe you have to choose a very small lens so that it fits to your system. There are, of course, other things as well. Mechanical stability. If you have laboratory use with always the same constant temperature, no vibration, every lens may work. But if you have an application, maybe outdoors, maybe in a car or whatever, or at the street, at a toll system, there's huge vibration. There is a lot of temperature changes, day and night, humidity, dry air. You should not think only of Stuttgart. You may do your business in the desert or in the cold. These are also things that need to consider when you are choosing your lens. And this can decide about success or missuccess of your system and your project. Do you need a zoom? Do you need different focal lengths? Do you need an exchangeable iris? Do you need a fixed iris? Fixed iris has advantages in mechanical stability, for instance. These are all questions that you should ask when you are choosing the lens. Not only the focal length, not only the F number, not only the price. Price, of course, is also important. Maybe your project justifies only a certain price limit you have to take care of. And also, very important and sometimes forgotten, availability. If you look for something special and you need to deliver your system tomorrow and the lens is not available, you have lost. So take care as soon as possible. I could talk in detail about all these points. Unfortunately, we have a time limit here, so I cannot speak 3 hours. I can speak 5 or 10 more minutes, so I have to concentrate on a few points to give you some examples. This is one example how lenses may react on different object distances. So you might have an application nearly in infinity, let's say a traffic application or a space application, or you can have a close distance application, something that you see here. The same lens does not work well in both cases. This is an example of MTF curves. This is a characteristic and a method to show performance of lenses. The simple rule is the higher the lines, the more even the lines, the better it is. On the left side, you see the graph for a working distance of 500 millimeter, typical industrial application. The lens performs very, very well. If you take the same lens and you use it for a traffic application or a space application in infinity or close to infinity, then you see a tremendous fall down of performance towards the edge of the lens. You may not see this in typical lens brochures of many companies because they tell you only something about general line pairs and resolution, but don't tell you the parameters where they are valid. We show parameters for close distance, for far distance, and of course you always can ask us, but please be aware, a lens does not work the same in all circumstances. It depends really on the specifications under which it's used. Another example is the spectral range. You know, most of the sensors used in the imaging industry are sensitive from about 400 to 1000 nanometers, so visible and near infrared. It can make a huge difference if you use a lens only in the visible range or if you use it in the visible and near infrared range. That's example, again the same lens. In this case, it's the same working distance, so this is the same specification, but in different lighting conditions. On the left side, you have the lighting in the visible range, so from 400 to 700 nanometer. This is the range where this lens was optimized for, and you see the high and even performance from the edge, from the center to the edge over the whole sensor area. If you take the infrared cut filter out of the camera and you use the full spectral range from visible to near infrared up to 1000 nanometer, then you see the lens was not designed for that, and the total performance significantly drops. So, also here again, choose the lens depending on your specification. Not every lens is equal, and not all characteristics like these are shown in the brochures and in the data sheets that you see all over the world. Look in detail, ask the lens manufacturer if he does not offer the data, ask him that he need to do, or choose a lens where you know what you get. That's a very interesting characteristics. Many people do not know. Most of the sensors are equipped with micro lenses on the pixels. So each pixel contains a micro lens which concentrates the light on the light sensitive area. That's a great idea because the sensors are more light efficient. A disadvantage is there's under certain angles, typically at the edge of the sensor, you don't have any more the perpendicular light, but you have something like this coming from the lens. It doesn't hit the light sensitive area of the sensor, and in the end you get dark corners. This is an example without micro lenses and the effect with micro lenses, so to the right and to the left you get shading. And this happens if the lens and the sensor don't fit together. You should need to understand if your sensor has special requirements regarding chiffre angle, as it's called, and then you can choose the lens which was designed with a low chiffre angle. Then you can avoid such effects. And the last, this is what I said, environmental conditions. Standard lenses are well suited for standard conditions like here. But if you have an application with very high mechanical stability demands, like auto applications in cars, in trains, Or like measurement applications, where it's very important that you have a very stable image on the sensor, that the image doesn't shift by tens or hundreds of microns. Then you need special lenses. A standard lens won't keep the image as stable as it's required. The standard lens would not withstand the environmental treatments as required. So you need lenses which are ruggedized or stabilized. Ruggedized means a mechanical stabilization, that it doesn't fall apart once it's treated under vibrations and stuff like this. And stability means the optical axis remains in maximum constant on the sensor, which is very important for CD applications. Also here, think what your application requires in respect to lenses. Think during the first design phase of the vision system and choose the appropriate lens, and only so you get the most out of your vision system. It's not only important to use the right camera or the right illumination. Consider the lens together with these components, and in the end you will be more successful. Your system will perform better than if you would neglect the lens and would keep it at last. Thank you. This is to an end. I could tell you much more about lenses. You can visit us at our booth, of course, and you can ask questions. You can ask questions here. You can get later to us. I really would love to tell you more about lenses, because my feeling is that the lens is very often the most underestimated component in the vision system. Thank you.
So thank you very much. So hello again. The idea of the landscape of synthetic data. So I have worked tremendously with synthetic data, with inspection planning, with virtual design of the inspection systems, visual inspection systems. And the question was always, okay, what is there? The topic has been hot for the past 4 to 5 years. It has been like steadily rising. It is not completely new. It's been there before. But with the rise of AI, with the rise of processing power and so on, it is back. Now, of course, it's the AI that is usually the main driver of things. And the thing with the AI in the industry sense is, the first thing is, it will solve everything. AI is here for us. And then the next step was like, oh, but we cannot really trust it. Do we know how does it work? It's a black box. You know, people are not really happy to use it. And then when we managed to convince them that it's fine, it's not going to do anything to you, and they were like, but we don't have the data actually needed to train it. I mean, it's nice to train the AI for everyday situations where you get abundance of data, too loud. But the moment that you step into the industry, the data becomes extremely restrictive. Now, this was the idea. With AI project, it is very simple. You have the data, you do the training, you get the results. And many of us working on projects promoting AI to industries, basically this is how we promote it, because this is the ideal idea. What it comes out in the projects often is that this expectation turns into this. So the pipeline is much longer. And as you can see, most of it's data. Either you have the data, but you have to label it. Or you don't have the data, so you have to acquire it and then label it. And then how do you label it? Do you trust people who labeled it? Is it correct? Is it imprecise? Is it pixel-wise? Is it image? How long does it take? Who is going to do it? The person on the line doesn't really want to do it because it's not their job, and so on and so on and so on and so on. And eventually you come to the training. And you're like, okay, I have the data. I have my little data set of 300 images. I'm so proud. I'm so happy. And then you start training and you understand, I need more data. Now, it is because of that whole pipeline and those red parts of the data problems why the synthetic images are here. The data challenges in general, it's about 3 things. The accessibility, can we actually get the data? The quality, once that we have the data, how good is it? And of course, consistency. Because let's have a typical production line. It's running. You have a supplier of a certain material that is currently used for producing this product. And you have set up your imaging system. you're acquiring the images, and you have a snapshot of, if it's a fast production, 1 week, if it's a slow production, maybe a couple of months even. And within this snapshot, you will only get the most frequent defects, and probably of only one kind of material. But what happens if the material supplier changes, which happens, and the product changes completely, and suddenly your solution doesn't work anymore? So the question of the data is not only if we have it, rather that what we have, is this good enough? This is why we have the synthetic data, and everybody's talking about it, at least in my circles, but I can admit I'm probably in a bubble. But given by the amount of people here, you have heard about synthetic data. Who has heard about synthetic data? Hands up. Cool. Who has heard about it before this talk? Awesome. Who has used it? Okay, promising. But the whole point is, like, you get probably bombarded with different kinds of input from different sides. AI can solve everything, so that means AI can solve the data problem. Potentially. Or you get the information, no, not that, just rule-based, just computer graphics, we want to know what's happening. Maybe. And you, as the final user, you have to decide, okay, which way am I going? Which flyer am I going to believe? Which group is the loudest when talking about how awesome and efficient their solution is? The point of this talk today was, I will show you what my group is doing, of course, but the point was to give you kind of an overview of what is happening, and I will try to pack it in within this probably like 10 more minutes. So the first thing is, what is the rules-based synthetic data? Rule-based synthetic data assumes that you have computer graphics pipeline that is based on a set of well-defined rules and assumptions that are used to generate the synthetic data. The images are realistic, but you have a full control over the whole pipeline. And then you have the generative AI. That means that you have a model in the background that has been trained on a set of real occurrences and is being used to generate new data in variation that you want to be able to train further AI. Sounds great. What usually is the question is, does this really work? And okay, we had the AI hype. Is this the next hype? Is synthetic data the next hype? Well, I've been in this domain for the past 9 years, and I can guarantee you this is not a hype. And the research that steadily grows and goes into different domains and challenges of the industry and assesses how can it be used and where it can help consistently shows that it is helpful. It is not without the flaws and is not without some different challenges, but so is every application. But definitely, it is not just a hype, and it's most definitely something to be used. Can someone take a picture? The crowd is awesome. Like, there is a huge crowd here. It's great. And this is something that people, you have a person selling you the synthetic data, and the other person's like, yeah, sounds good, sounds good. But I mean, there's this elephant in the room they did never ask, like, can I trust your data? Ask that. Always ask that. So, okay. When you are faced with synthetic data, what do? There are so many questions, so it's like, okay, which one do I take? Rule-based, generative AI. What about the domain focus? What is domain focus? What about the domain gap? What about the open source solutions? Can I use something for free? Because we all know, okay, that would be great if I can just, grab something off of internet, try it a little bit. Okay, there are so many new companies all of a sudden. Which one do I take? Which question do I ask? What about the freeware? Maybe there are some very strong companies that are offering some freeware. What do? I will give you just a brief overview, but let's start with this. Rule-based or generative AI and the domain focus. Okay, is this a bicycle? Hands up. Okay, there are some people who are not sure if this is a bicycle. Good. Is this a bicycle that you would sit on and drive? Assuming that you can drive a bicycle, come on. Yeah. Okay, do you think this bicycle is safe? Yeah? Yeah? Okay, those who don't think, care to say why? Any takers?
just look at the front wheel. There's something under the brakes which I would not trust sitting on.
Good point, but unfortunately that is just a reflection. Any other takers? Chain. Nice. How many people do we have here? I would say 50, 60. Are we going towards 100? I don't know. I'm bad at crowd counting. I'll leave it to AI. Exactly. This thing is missing. Has this been generated by a human or an AI? Who is for human? No takers? Who is for AI? So this has nothing to do with AI. This is just fact on people. The guy asked the people to draw a bicycle from their mind, how they reminded. Let me tell you, some of those people were actually professional cyclists. These are their drawings. And this is what the guy did. He did the 3D models based on their drawings. Now, I would say that every one of you has seen a bicycle. It took in the whole of about 60 people looking at this right now, it took quite a bit of time to figure out that there is a very important part of it missing. And this is the problem that we have similar with the generative data. It's about the context, it's about the focus. You need to know what you're looking at. And when we are talking about the industrial data, let's say you have the generative model that generates your data. How do you know that it's correct? You need to look at it. And if we cannot see if the bicycle is correct, how do we make sure that actually these images, so this up there is an actual milled surface. This is what the generative model generated when asked, create me some variation. It's about the context. What the model has been trained on. Does the model know how to generalize? How does it label the images? It's very difficult to create labels with generative models. Always ask how this was done. And then is the question of scalability. Okay, you want to scale to different domains. You want to scale to different surfaces, different materials, different defects. How do you do it with the generative AI? And then just another thing is, when you look at this video, it looks nice. But if you look really close, so this is generated by Sora by OpenAI. You notice all of a sudden that those legs are kind of floating like tentacles. And those tentacles have little things on the top that it's not supposed to. And at some point, there is an escalator of little things. It's not supposed to be there. The generative AI has no idea about the physics, the underlying physics. And if you want to use synthetic data that is reliable, you want to have this. You want to have this control. So in the rule-based simulation, you have the context, you have the scale, you have the realism. This is how we do it in my group. We have a rule. We have a parameterization point saying, OK, what is it that we're parameterizing? Is it the defect? Is it the surface? Is it the texture? And then we develop a mathematical model of it. And this is what we use for variation control. So we know exactly what is happening and how scalable it is. This is the framework. So you can set up your cameras. You can simulate the lens, the camera, the position. You can set up defects. You can say, OK, what is the variation? What are the parameters? And you go further to simulate this. You get pixel-precise labels. And you know exactly what is in the picture and what should it be. And then the question is, how real is your data? It is as real as you find it to be real, because the realism doesn't have a real measure. And I'm willing to argue with you on this, just not right now because I don't have the time, but afterwards, please do. The problem of the realism measure is it's still on the eye of the beholder. For us, this is real. The question is if it is real for the network. This is why we have defined two types of realism. A priori quality, a posteriori. A priori basically says, is the context with the rules, how it has been designed, valid? And a posteriori says, OK, is the network that is actually trained on these images correct? So all of these are real use cases, and all of these have been simulated with our models. Then you can use another thing that is called domain randomization. That means that you use the control and the variance to exceed. You have the realistic images, but then you exceed the features to show something that is physically possible but very unlikely. This helps the network to learn more. And then finally, what to use. This is just a small overview with the perspective on industry, really strong industrial option. And if anyone, there is a lot of new companies spiking up, so please ping me if you know some other companies that I did not involve here. It's not on purpose. The point is, focus is on industry, on production. So you have the dataset generators, you have the rendering engines, you have the NVIDIA Omniverse that is very popular right now, and you have the whole number of proprietary solutions. So the question is what you want. Do you want to implement it yourself? You can use the rendering engines, you can use the dataset generators, you can use NVIDIA, you can use freeware rendering engines. But this will cost you time and resources, and you will have to have an expert doing this. Okay, so you say, fine. Let's focus that I don't actually spend too much time. You still have Blender, that is cool. But you are shifting about the question is, what is it that you want? Do you want scene understanding? There is a number of options. And then scene and understanding, more or less, every company producing industrial synthetic data can produce you good data for scene understanding. The question is of the context. What is the context? It's the world surroundings. What is the scale? The scale is the geometry of the object. And what is the realism? Well, the geometry has to be right, the world has to be right, but the very fine details, it probably won't matter. The network will extrapolate anyway. And then we are coming to the surface inspection. There, the context is actually the acquisition setup. What do I expect on the surface? How will the defects be? What is the level of realism? How are the defects looking like? Does this make sense? Is it appearing where it is supposed to appear? And with this, again, I'm happy to say, like, just hit me up. My group is joining together with the startup Medapsi that won the startup of the day yesterday. So we will also be there on the booth because we are bringing the rule-based approach more to the industry. And then one last slide. That was that slide? Okay. One last slide. Take a picture. When you're talking to a company or anyone doing synthetic data, these are the good things to ask. If you're using synthetic data, these are good things to do. They're general guidelines. It is nothing written in stone, but it has shown to be useful. So use it, and all of your experiences, please do contact me. Here's my contact data. Please do contact me. Tell me what's your experience. Tell me about your use case. Tell me where it hurts and where it doesn't. And yeah, I'd love to take it from there. Thank you.
My name is Forad Stolz. I'm CTO at Photoneo, and I will be talking about new developments that we did in our products that are basically circulating about these use cases. It's like when the light doesn't behave with the objects and when the signal perspective is not enough for handling. But before we start, I would like to introduce our company briefly. Photoneo is a provider of 3D sensors, like hardware modules for beam picking and robotic applications. Additionally to our 3D sensors, we are also producing software that is used for robotic intelligence, beam picking, but not only beam picking solutions, where we apparently are using also AI principles. We have about 8,000 solutions worldwide. We operate through distributors and partners, and we have about 310 employees and more. The number is rising, and we have apparently worldwide operations. We are leader in vision-guided automation, vision-guided robotics. Here are a couple of our partners and a couple of little videos just to give you a flavor of what we are doing. We are providing in all these installations and many similar installations robotic vision, so we call it robotic eyes. And then the software that we are developing is robotic intelligence. Our portfolio consists of these three pillars: 3D sensors, beam picking software where AI is taking place, and also digital twinning software. It may look standing out a little bit, but I will show later like how does it nicely fit together. Our camera, MotionCam 3D, some of you are familiar. Some of the companies here in this hall are providing here. Rauscher has even demonstrator with our camera. Is probably the most advanced 3D camera that you find on the market for area scanning, 3D area scanning. What's so important about it or so different? It's because it is located in a gap of current 3D sensors, which means that it can combine highly demand or serve highly demanding applications by providing high quality point clouds, but at the same time it's not really affected by motion in the scene. So if there is any motion in the background or in the foreground, or if the object itself is moving, it doesn't have to, but if it is, then MotionCam 3D can still provide very good data. And it is here an example how such data from MotionCam that's on the right side may look like. It's a snapshot system. The scene that you have there is not an industrial scene, but it should illustrate that even if the scene is moving and it comprises many different material types and object types, it is still, MotionCam is still capable of providing very good high quality point cloud. Compared to other two competing technologies that we picked. There are other technologies, 3D technologies, but just for the comparison, time of flight that is typically applied when you need very quickly undistorted data. For example, for some logistic applications or robotic handling, you get the data quick, but typically it's very noisy, and also resolution is still not the greatest. While structured light approach is great if you have a stationary scene, if the objects are not moving, but it takes time to capture that, and if the objects are moving actually during that capture time, structured light approach is suffering from severe artifacts. So if your application, but I mean, you can, MotionCam is very good that you don't need to think anymore about, you know, the type of applications you are dealing with. You can just take it as a, like now in every pocket there is a camera. You don't need to think really about, you know, is it dark, is it bright? You just press a button and you get a nice point cloud. With MotionCam, you are there. It's a really significant leap in the 3D development. And all this is thanks to our proprietary CMOS sensor that our company has invented and developed, which is implementing something that is very different from what you see around here. Here at the Vision Show, there is like lots and lots of different cameras. All of them are taking images, either using global shutter or using rolling shutter approaches. But our MotionCam 3D and Compass sensor is implementing something that is called mosaic shutter. Why mosaic shutter? It is because pixels on our sensor are organized in a mosaic, similar to Bayer pattern. But those groups of pixels can implement different temporal sequences, temporal patterns. So we can very flexibly program those groups of patterns. It's just an illustration, which are then used to capture multiple structured light patterns in a snapshot. Here on the left side, you see a dynamic process. I was dropping a ping pong ball on the table and capturing this process with a standard structured light system that is capturing frame after frame after frame. And obviously when the ball is falling during that process, you get, you know, patterns projected in different time phases. While with MotionCam and Compass, this is done in a snapshot, and all the patterns are consistent, and the good 3D data can be then recovered from that. Here an illustration how a point cloud may look like if you take this process and you drop the ball, you take a standard sequential structured light camera, you get a distorted point cloud. So at most you might be able to remove those artifacts. But actually with MotionCam you have a very crisp, very good quality 3D point cloud, even if the object was moving during that process. Because actually it wasn't moving because we took it in a snapshot. Here, very brief and quick illustration, like what's the trick? Maybe some of you are asking, like, so what's the magic? Is like our devices are stereo systems. We have a projector and a camera unit. Here in this illustration, we see how a standard structured light system would work. So there is a projector on the left-hand side that is modulating the light during the sweep, and a global shutter camera is looking at the scene, and when the frame is finished, you get a nice stripy pattern projected onto the scene, captured. But obviously you cannot parallelize this. You cannot take multiple frames together at the same time. So what can be done differently? With a parallel structured light and mosaic shutter, we are essentially exchanging the role of the camera and the projector. So the projector is no longer modulated. Projector is just basically sweeping with a laser line from left to right. And the camera, during the exposure window, is basically closing and opening the eye. And this can produce a pattern, the same pattern as with a standard structured light approach. But this can also be parallelized. So if you have a sensor that can actually combine multiple of those patterns together in different pixel groups, you can capture multiple patterns at the same time in a single sweep. That means with our proprietary sensor, we can capture in a snapshot nice 3D point clouds, which is great. That is really cool. Here, an example, again, about the data outputs of our motion cam. It also comprises a processing board, NVIDIA Jetson. Everything is processed directly on the camera, so the camera is sending out already a processed data, be it a depth map, be it a texture, or a 3D point cloud, or surface normals that are directly computed on the camera, but there can be also other outputs. What is important, we are probably the only 3D company that is currently supporting GigaVision protocol, fully integrated with standard softwares. So that means you are getting this basically on a golden platter, you know, out of the sensor without very short latency and without any need of post-processing. But this is just a sensor, this is just 3D data. But when it comes to the actual real applications, you know, this is what we are currently maybe over the last 2 years facing with our customers in logistics applications. Imagine you have a warehouse. There you have, I don't know how many thousands of SKUs. Many of them are pickable. Many of them are not or used to be non-pickable. And now, like, what can be done differently? Typically, light doesn't behave very well on these objects. But we managed in last year, in one of the latest releases, we have introduced new coding strategies that is then allowing us to scan even transparent and translucent objects very nicely. I'm not saying that we can really scan a crystal, you know, glass or something like that, but many SKUs from warehouses we can scan. Now they are pickable. Now we can really handle them, localize them, and pick them with our robots. Here this slide should give you again kind of a flavor of what's going on, how this is actually happening. Thanks to the modularity and flexibility of our sensor, we have introduced new coding strategies that is basically going from this type of dense codes that are not really making it possible to distinguish different layers of the transparent object to a code that we call sparse. This is just an illustration. It's not the actual code that we are using, but it should illustrate like what's happening over there. So all of a sudden, with a sparse code, one can see, you know, the background layer, foreground layer, mid layer, and actually with the help of good algorithm, one could go into something like tomography even, that you would be able to build up not only the outer surface, but also inner surfaces and so on. We have introduced these novel codes, and these are just few examples of what's possible, what was possible before and what's now with the new coding strategies. With the help of these strategies, we are also able very efficiently suppress something that we call interreflections. Imagine you have these L-shaped parts that are essentially reflecting on each other. You are illuminating one local, you know, patch, and this one reflects to the other one. Codes are getting mixed. With the help of new coding strategies, we can suppress interreflections very efficiently, which makes many objects pickable. Also with dark and glossy materials, we pushed, thanks to these new coding strategies, the scannability. Imagine you have an automotive part that is really dark and glossy, that is essentially acting as a black mirror. You don't get typically in huge areas any response or very like weak response. Here with the new coding, we can optimize processing settings. We can capture very nicely almost the entire object. And one of the also latest developments is a new ambient light suppression that is thanks to, again, the flexibility of our platform and our way we control the sensors. We can scan in the ambient light up to 100,000 lux with a very good, recovery of the surface. If you are interested in this technology, come over to the other hall, to our booth. And now, very, very briefly about when the single perspective doesn't suffice, right? We have our digital twinning software called Instant Meshing. It supports all these scenarios like custom manual marker board or rotary table or robotic capture of the multi-view with the help of motion cam. You do not need to really stop. You can really just go around and scan. And also big gantry systems. With this, you can nicely build, 3D models of small parts, but also huge objects like cars, for example. But what is it good for? Lately, we have integrated this into our BIM Picking Studio software. Now you can very easily utilize the power of robot, camera, and hand-eye, but not only hand-eye, also static multi-view that allows you to pick very successfully also parts like these little L-shaped thin metal objects that if you are not lucky, you are looking from the perspective of the edge of the object and then you basically see nothing. You cannot localize it. But with the help of multi-view, thanks to motion cam, you can do it really quickly, actually in a time of single scan with other systems. We can, in a real time, merge those multiple viewpoints, get a point cloud like that one, and we can localize these parts very, very efficiently. Again, if you are interested, you are most welcome in our booth. So, conclusions. If the light doesn't behave, we have introduced our new coding strategies that are allowing us to pick maybe not 100% of objects in a warehouse, but maybe 90, 95, 85, which is really big leap compared to the previous. And if a single perspective is not enough for our BIM picking solution, we have introduced now a very nice extension that can merge multiple viewpoints, again allowing us to pick many, many objects. If you are interested, you are most welcome to come over to our booth. Thank you very much.
Yeah, welcome to my talk about digital twins in machine vision applications. My name is Sven Wanner and I'm from Artificial Pixels. In my talk I will give a short introduction into, or a quick definition of what I mean with a digital twin in machine vision applications. I will go over some typical use cases or application areas. Will show you a little bit about the value a digital twin can bring to your project. And in the second part of the presentation, I will talk about maybe one of the most famous topics related to digital twins, the generation of synthetic data. The Digital Twin Consortium defines a digital twin is a virtual representation of real-world entities and processes synchronized at a specified frequency and fidelity. This is a very broad definition, which is normally good for a definition. For the sake of this talk and digital twins in machine vision, I want to make this a bit more concrete and say a digital twin is a simulation of sensors, objects and processes applied to these sensor and objects. This means digital twins are, in our view, not just 3D models, but the entirety of relevant data streams produced by your vision application. Typical application areas of digital twins are system design and risk minimization. If you start your project really from the beginning with the digital twin, it brings you a lot of benefits for both the hardware development and the software development. For example, your hardware team can start right from the beginning to evaluate their hardware planning. Would it be better to have the cameras here or there? Would it be better to have the lighting here or there? So it really helps to virtually optimize the hardware system, and thus you can achieve some optimizations before the hardware was built the first time. And also your software team can early start development and parallelize this with the hardware team, which normally shortens your project timeline quite drastically and, as said, minimizes risks of failures. A second application area we call on-demand simulation. What we mean with that is that we more or less see the vision application as a computer game. So the simulation then is built in a way that you can integrate it in your software solution and trigger it live with your software and get the data back as you would work with the real-world system. And this has, of course, a lot of benefits in some applications, but also for your development team. Each developer can have its own vision system ready to use anytime to experiment or whatever. And as said, one of the most famous application areas is synthetic data creation. In this mode, we normally use the digital twin not in a live interaction mode, but use it as a data generation machine. So the purpose then is to vary all the free parameters of the system in a way that you can, in a smart way, create big data sets to train models, for example. And with this synthetic data created, you can, of course, start pre-training a model. You can extend your real-world data sets or handle edge cases. And synthetic data are also quite nice to analyze your real-world data sets or gain deeper insights into your overall problem. And to summarize this, the benefits a digital twin can bring to your project starts really in the beginning of the project. You can early kick off your project. You can start your software development early. You can optimize your system quite well virtually and with really low costs and in short times. You can use it as a live interaction tool. You can create big amount of data at scale. And one of the most overseen benefit of a digital twin is when it comes to changes. When your customer starts and suddenly says, okay, I want to use this box instead of that, or there's another camera type, maybe cheaper and better, could we use also this camera type in our project? Then using a digital twin or simulation, you can quite easily and very fast adapt to such changes. And as a cherry on top, digital twins also can produce a lot of nice advertisement material or info material for your customers. Let's now come to the synthetic data topic. I quite often use this image to demonstrate one thing, because often I meet people that are either skeptics or enthusiasts when it comes to synthetic data. The skeptics say, oh, synthetic data, this will never work, it's too unrealistic, will never work in real world problems. And the enthusiast says, oh, cool, we can do everything with it. And as always, the truth lies somewhere in between. And in a couple of slides, I will show you how synthetic data actually can look like, not like this. But first, I want to quickly talk about how we can make synthetic data that actually works. And for that, I prepared a couple of slides to explain an idea. So here we see just a stupid, very simplified data set, 2 dimensions, 2 features. It's already annotated. Let's say blue is not okay, yellow is okay, or the other way around, doesn't matter. The thing I want to tell you with this plot is real data normally have a certain distribution in the feature space. And if we would train an AI model on such a data set, it would try to find a function in this feature space to separate these distributions optimally from each other. And that's what a model normally is doing. And now let's add some bad synthetic data. We added some synthetic data in these small red circles below. And why are they bad? They are bad because of 2 reasons. First of all, you immediately see they don't have a normal distribution. They are really in a really tiny area in the feature space, which normally means they are kind of too perfect. There's not enough variation in the data. And the second type of problem is they are quite off from the distribution centers. So both of these problems are very common with synthetic data. And if we now apply the model we trained before, oops, our synthetic data works quite well in this example. So does this mean our synthetic data are good? Of course not. If we would train the model just on the synthetic data, then this could be a possible solution, and you immediately see it wouldn't work in real life. And this is the main issue that happens with synthetic data if you don't do it correct. But there's another problem. in the red ellipse, I added some new real-world data points that we don't have in reality, because these are these typical hard-to-capture cases. They are really hard to capture, really rare occurring events. And in reality, we don't have this data, but your distribution would look like that if you would be able to capture all of the data you need. And if we apply our model that we trained on the data, we immediately see this is where data models fail on these hard edge cases if we don't have them in our data set. And then this is the image what I want to show you how good synthetic data should look like. So we see we have two very important parameters. We have these normal looking like distribution of the data. We have the same distribution centers, means the images are really similar to each other. And if these two parameters are valid, then we have a very, very big chance, if we generate edge cases with such a digital twin, that we really reproduce what we would measure in reality. But another point is, how can we use synthetic data to really benefit our model when we use them? And for that, I want to illustrate it with these 4 pictures. Question to you is, are you able to extract any information of these 4 images? And I promise there is an information hidden in these 4 images. I will not wait for answers, because I'm quite sure no one can do it. But if we change the representation of the data and maybe arrange them in a 3-dimensional volume and interpret the 3rd new dimension as the time, you will immediately be able to extract the information. As a human, what we are doing, we find the hidden statistics now through the time dimension, because we see the statistics on some pixels is very varying and on others it's static. And an AI model is exactly doing that. It searches for the hidden statistics in huge dimensional spaces. And how can we help a model to learn these hidden statistics better with synthetic data? And for that, we end again with this image we have in the beginning of the topic. So now we see how synthetic data can look like. You see now on the left side images captured with a normal digital camera, and on the right side images generated with our synthetic data pipeline. And you see we can perfectly reproduce the real world data, but reproducing the real world data does not make so much sense, you would say. But the only thing I want to show you with this is that we are able to generate data points that are really, really close to the real distribution. And if we can do that, then we can, in the next step, start changing things. So if we now start in the digital twin, change the illumination, we change the geometry, we can say we change the color of the objects. If we start changing the things the model should learn that they are not important, then change it. Change it as much as you can. And this will help the model to learn what is not important for me. You can also, of course, add defects and imperfections, and all of these possibilities you have having a high-quality digital twin that is able to produce such synthetic data. But changing colors and everything I showed you before, I hope you can see it. Maybe it's not optimal here, but all of these changes are happening in the image domain on the model. But there's another domain where variation happens, and this is on the physical level. Optics generate defects, generate changes. Sensors generate sensor noise, very specific normally to the sensor you use. And we also simulate that, and you see on the left side, or if you would be able to see it, you would see this is a crop from the real image, and you see the sensor noise, you see the optical defects. The middle image is a pure rendering, and it's too perfect. You see crisp, sharp edges, you see no sensor noise, and after our simulation pipeline on the right, you see that we can get really, really close to the real-world distribution. And this is how we can really help an AI model to learn what it is missing on not complete real-world data sets. So I think I was quite fast now. Yeah, 1 minute faster. So I'm open to your questions.